Who cares about tilt?
And I guess the other point is, did you guys get your problem set created? Did anybody get theirs? Okay. So, I guess what we'll talk about today is, I'll talk about what I think you should cover on the exam, and then you can ask questions.
You think you know what's on the exam?
Any other questions before we start?
You only got 10 minutes of recording time in there.
So, mostly this is going to focus on this internet layer, right? So that's mostly what we covered since exam 1, except for one topic, spanning tree, right? So that is something you probably should know, spanning tree protocol. And I guess with this, the question is like, why do we need this? Anybody remember? Loops, yeah, right. We have this issue of loops, and why that's a problem. How does it work? Anybody remember that? You know, essentially, I mean, you should. We didn't really go into the structure, but you should, if I give you like a simple network, you should be able to understand like what the spanning tree looked like in that, right? So it was a distributed algorithm. The central around the tree formed around the lowest ID, right? And basically we broadcast our distances to the root, right? This is the root. And then we just disable ports based on what ports were not needed, right? That was kind of the approach we took. Well, what are the problems with this? Anybody remember?
If you have to lose another connection, you have to do multiple things.
We have to if something goes wrong, we have to reconfigure. And what's wrong with what's the problem with that? Yeah, I mean the network's down, right? So that's a bad thing, right? So understanding kind of that challenge, why we're doing this, and what are the trade-offs is I think a good thing to know. So that was really the only thing that came from the previous link layer. So the rest of it should be on internet layer stuff. And I guess where we started was talking about kind of IPv4 addresses, right? And so I think the key thing from IPv4 was the addressing, right? So specifically, you know, what are the portions of an IP address? Yeah, we have a net mask. The address will essentially have a network component and a host component, and this is all determined by the net mask, right? Right. So we have this notion of, you know, dividing the network and understanding, you know, the address based on this. So it's a hierarchical address, right? And there's kind of the CIDR address scheme, which is a way to define this based on a net mask, right? So really, CIDR is one way to define the network and host components of an address based on a net mask, right? And you've done examples of that, so you should be able to do an example on the test. That's almost certainly going to be there. I've never given a test on this and not put this on there, so I'm not going to start. I'll start that now, I guess. So You know, because you could also do classes, right? We talked about classes, like class A, class B, class C. Those aren't really used, so I don't really care if you know those, but you should definitely know CIDR because that's like important, right? So I just wanted to, those are actually kind of competing approaches, right? CIDR or classes.
What do you mean by doing a CIDR?
Like computing, like if I give you an IP address and say like, what's the range for this, right? You should be able to compute like what the range is, what a /20, you should know what a /26 is versus a /20 versus /20. You should know, like what addresses maybe would be within a range, or what addresses will not be within that range, right? So if you can just take basically this an address range, or if I give you a range, compute the CIDR range for that, right? Basically, you should understand how this converts to a set of addresses, right? And what addresses those are, and do the conversion from there and back. I clarify? So somebody asked a question like whether I'm going to ask you like specific fields. I don't want you. I'm not going to like make you draw the IP frame or header or something like that. But I think like within the IP, the header. What are important things within this IP header? The addresses are. I mean, understanding how big are the addresses and the size, right? So you should know like I don't really care if you know there's a checksum in the header. It's not really used, right? But you should know the addresses and stuff like that. What else is important in this? Huh? Addresses, source and destination address. Both of them. Type of live is kind of an important thing because it deals with routing, right? That's actually an important thing when we route because it prevents our packets from routing an infinite number of times, right? Because we can't really do spanning tree on the internet because no one's going to agree on how to do it, right? So something go wrong and stuff to route forever. You have time to live to prevent that. What else is important in the header?
Fragmentation information.
So fragmentation, right? That's something we talked about a little bit. And there's like 3 fields. We talked about like the identity, the offset, and then a flag set telling the fragmentation. I'm not gonna expect you to remember those. But you should understand what's the point of fragmentation?
Accommodating
What is it?
maximum transition units.
What's that?
Accommodating different maximum transition units.
Yeah. It's based on this. We have to take this IP diagram. We put it into a smaller, often link layer, and that link layer will have a MTU, a maximum transmission unit, right? And so we need to deal with this because often the IP diagram can be like I think like 65,535. I think I should use this. That's going to be bytes, and our Ethernet could be like 1,500 bytes, right? So it's obviously not going to work. We have to be able to fragment, right? Stuff. Take one packet, split it across a bunch of other packets. So you should understand the concept. Maybe not exactly how it's implemented is not that important. So I think those are the key things regarding IPv4. Any other questions on that? So what is that for?
Assigning addresses?
Yeah, obtaining addresses, yeah. Obtaining IPs, how do we obtain? So how does that work? Anybody remember? There's a problem, right? Because we don't have an address. We're on a network that all we know to start is our MAC, right? If you bring your system on, you have a lot of, when you came onto the network, all you have is like your MAC. So how do we determine an IP, right? So we have to send a message out to who? Huh? We have to send some broadcasts, right? and hopefully what's listening, we have a DHCP server that should be listening and then have some allocate, some sort of address pool, right? And then this hopefully can give it what we call a lease, right? An address lease back to the client, right? That the address can then that client can then decide to use that lease. And what information might we need in this to use an IP address then? Just the IP? Huh? A subnet? I mean, how would they define that?
It's on the router.
They don't provide us. How do you define a subnet?
NetMask.
Yeah, you'll probably have an IP and you'll probably get a net mask, right? Because those two together will provide a subnet. What else might you need?
Port?
Port. I mean, port is, this is gonna need a default port, right? So it's gonna need to do something based on this net mask, right? Which is, I mean, you might want to talk to systems outside of that network, and what do you need? A gateway, a router, right? Right. Or often, we haven't really talked about this much, but why my writing's going very straight, but or maybe a DNS address too, so you can resolve. There's a local address, right? So, you know, if you're on WC's network, you'll get all of these, right? From the yeah.
So you said the netmask was with respect to the gateway router?
Huh?
So the netmask is within the router's IP range?
Yeah, the router. This router has to be within the range of the subnet, right? This is going to determine kind of the subnet, right? Based on these two, you know, from project, whatever the last programming assignment was, you had to compute that, right? You knew an IP address and a subnet, and then you had to figure out like what's in my address space and what is not in my address space. Then based on that, you would determine who to send a packet to. Do you send it to that host or do you send it to your router, right? Any other questions? Does that make sense? So the HTTP is important. Let's talk about NAT, network address translation. So what's the point of NAT? Huh? Why?
So you can have a different addressing scheme inside the network than you do outside the network. You can
Yeah.
transfer between the two.
We can map. Often it's really the key is to, I mean, obviously it's translating addresses because it's network address translation. But the point is usually you want to map, you want to have some mapping of external addresses to internal ones, right? But
Maybe a run.
huh?
Maybe a run, not just one thing.
But often because you want to share, or you want to maybe like use local or non-routable. You know, you can use non-routable. That's supposed to say non-routable. That doesn't. This should. Non-routable IP ranges, right? Like 10, that's something, or 192, that's something, right? So it helped use. So it helped kind of also helped conserve, right? IP addresses, right? Because we only need one external. So we showed how, you know, WCU has we're all on a big NAT right now. All of our devices are, and WCU has probably a few external IP addresses. I don't know, probably more than a few, but that all map to all of our real ones. So they have a couple of real addresses, but we're all on this giant 172 space, right? So we all don't have our own real routable IP addresses on any of our devices here, right? But what's another good advantage in that?
Security?
Yeah, security, right? Because really, because because devices can only talk out, right? You can only devices inside a NAT can initiate a connection. If you're outside a NAT, you can't initiate a connection inside because there's no translation table, right? So if somebody from outside a NAT tries to talk inside a NAT, can't do it, right? So that's a good thing. So you should understand how these tables work. How the table, there's a table associated with this. We did an assignment, programming, or a project, or a book assignment on this, so you should know how that could work and how to the mapping is performed. Yeah.
What is that third item there say?
This one?
Yeah.
Non-routable address, right? You can use these 192.10 dot whatever 172 dot whatever ranges, right? Or you can do real ranges too. I did. Maybe I did this thing once. Let's do this because it's pretty long. But I was doing some work in a research lab at my old university, and we had all these systems in this on this network. They were actually on the real campus network, so they had like real IP addresses, right? So let's say they had IP addresses 1.1.1.1 and 1.2, 1.3, and they were all connected to a campus router. Or this would be like in the building router, right? And let's say this is 1.1.1.1.4, right? And this was going to, and then this is our lab, but they're all on the same IP address, and this is like everybody's office, right? And they're all .5 and .6 and .7, whatever. There's a lot of systems how to fix them, right? So I thought like, what we'd like to do is make these separate, because I don't want people from the internet, you know, going and hacking our stuff in our lab. But the problem is like nobody knew how to change the IP addresses because they were hard coded in the devices, so we couldn't change the IP addresses. So I thought that's not a very good situation. So what I thought I'd do is I could create a NAT here, and I can give this like 1.1.1.1 or something as an IP address here. And I can add all these to, and I can give this interface 1.1.1.4, right? So I'm gonna NAT within the same range. And technically this works, right? Theoretically, it works because it's just an address translation, right? It's just gonna look it up in a table, so it works. The problem is, so I have to have a firewall that stops everything. So this is basically a firewall. I rebooted the system and I forgot to start the NAT, right? I set up the rules and I forgot to start the NAT. And then, so what was happening is, all the devices were just communicating based on their IP addresses, right? So what problem does that introduce?
There are more than two 1.1.1.4s.
Yeah, and which one of these works, right? So my device was saying like, everyone would ask like, who's 1.1.1.4, right? And sometimes this would say me, and sometimes this would say me.
Makes for some fun networking.
Yeah, and so when this said me, everyone's decided like, oh, we'll send all our packets to you, and my device wasn't routing anything, so they would just go down, and so like the IT people had a hell time, and then they let me know it was me. First I was like, I was like, this works. I figured it works. I don't know what went wrong. I realized it didn't start. If that doesn't start, then it's just doing all this dumb stuff. And so basically I took out like the whole building. Nobody could use it, and nobody could figure out what's wrong. People are mad. Anyway. Then we talked about IPv6, and so what is better about IPv6?
Bigger size of the.
Better address space, right? 128-bit addresses, right? What else is better?
Uses a CRC instead of checksum.
It doesn't use CRC instead of checksum, but it does something similar to that. It does something that it does the other way. You remember? What was the issue with the CRC, the checksum?
You can have errors mixing up.
But not. I mean, that's the true in general. But what's the issue with doing a checksum with IPv4 or 6?
The value of the checksum changes the checksum.
Yeah, every time you route the time to live changes, so which means you got to compute the checksum, and that's a hassle. So every time you routed everything, it's a bunch of you guys had to do the project 3 had to compute checksum, right? And it's a pain. You can think of that process. Every packet you're routing has to do that, which is dumb. So it just removed it, right? Removed. So basically, rather than making it stronger, it just says like no checksum. Because we have way too many checksums going on anyway, right? And CRCs. So this helps for, what does this help though? Makes routing a little bit more efficient, right? What else?
The addresses are generated from MAC addresses.
Well, I mean there's this stateless
Oh yeah.
auto config address. And where you can generate what portion of the address? You generate the host address portion, right? From this already unique MAC, which is kind of nice. This is a feature. It's not always done like that, right? You can still DHCP and stuff like that with IPv6, but this helps with configuration, right? Which is a nice property as well. Anything else? That IPv6 helps with. I mean, they do introduce concepts like encapsulated security payload or something like that. So they have some security, right, where you can encrypt a payload and have an identifier and SPI or something like that that you can uniquely people know how to decrypt it on the other side. But it doesn't really talk about how to do the security, but it supports the data necessary to provide the security, right? So I think that's I mean, we're going to talk about IPv6 very much, but those, I think you should understand like what are the key differences and why those are implemented, right? So then we move to like routing, and I guess this is kind of going to be where we'll end. And so we had a route table, right? Which is basically what is this? We're going to have the route based on either a we can look at we're going to look at an address now, IP address, right? And then we're going to assign it to an interface or maybe even a host if we know the host, right? So routing can it's going to be the table's going to be a little bit different than the switching table, but ultimately it's the same concept, right? What are the two approaches?
TV,
Huh?
TV underneath the state.
Well, there's broader, right?
You mean OSPF and RIP?
No, routing in general, right? We have two broad approaches.
Circuit switching versus packet switching?
That is more like that is like a type of like forwarding. Routing is that's usually more in the switching level, right? Yeah.
Intra-network versus...
Yeah, intra-domain or extra-domain. Intra-domain.
Gonna show his picture.
Alright, intra-domain.
I just want to make it pretty, and then make it.
And so where does link state in this inspector fall? Intra or inter? Intra. So we had link state and this inspector, right? So I think in your assignment you had to like actually compute one of these. Won't make you compute it, but I think you should understand like how they work. So what's the difference between these?
I think this is more efficient than this than black.
More efficient?
Yes.
Why?
It's something the group says something. interstate can carry you big or longer lanes.
Link state is more efficient. Yeah, I mean, probably algorithmically,
Yeah.
but I mean, it depends how you define efficient, because there's a trade-off, right? Like, yeah.
Distance vector is distributed.
This is like a distributed one, such that everyone sends around their vectors, and so they converge to like they send vectors, right? Well, they do this process send vectors, and then they slowly converge by learning better routes, right? And the other one, right? So we're gonna send these vectors, and we're gonna learn from the new vector, and then we're gonna update our route, and we're gonna send that around. And so we're continually going and learning new routes.
What does it say underneath distance vector?
It's distributed, and we're gonna send around. We're basically sending around the vectors, right? And we're gonna converge by learning better routes continuously and sending around our vectors, right? So we distributed in a distributed algorithm converge towards the route. Where what's different with link state? It's centralized in the fact that we have to do some sort of flooding of the topology, right? So we have to let everyone know. Everyone needs to know about everything in the network, right? And then we can do a basic, we basically so everyone knows the topology, and then that, but and then we can just do like Dijkstra's, right? Shortest path algorithm, right? So, two different approaches, right? And this is probably more efficient than this algorithm, but then this flooding is kind of a pain too, right? And so they're, So those are. And this is like OSPF, and this is an example of this is RIP, but we don't really talk about those too much. What's the difference between that and interdomain? What are we trying to do here? What's the goal? Huh? Of both of these?
Allow new devices within an autonomous system to communicate.
Yeah, we're doing it within generally this is within an autonomous system, right? And all these they want to find an objective, which is the what? The best path, right? Shortest, lowest cost, right? So what about intradomain? What's the difference?
How expensive it is to route.
Yeah, we have more. It's between. Autonomous systems. There's multiple. It's based on the goal is more based on what? Our routing decisions are based on what? Yeah, often we'll just call it policy, right? So that was like a big thing. Policy. I mean, policy didn't dictate everything, right? We did look at path, right? So we looked at path. So that was like what was it? Remember, we have like so path was important, but it wasn't like the main thing. And our paths maybe didn't necessarily have a cost. We like to pick shorter paths, right? Where these you would have like a path cost for everything, and you compute a best algorithm. Here, where it's like, well, this path looks shorter. It's got less hops in it, so let's just take that, right?
You say it's more like best effort than intradomain would be? Like more just like, okay, we have it and we'll send it out.
Yeah, probably. I mean, that's not how it's generally described, but I think that's a safe way to say it, right? It's like you're trying to find a route that works, and you'd like it to be less costly, and you'd like it to be short. But if it works, right? Because it's hard to just ensure packets get across the internet, right? And so we'll take paths that work. We're not going to be too picky about the shortest one. So yeah, so we talked about BGP, right? And we talked about, what were the two things that BGP advertised? AS path, which one did AS path contain? It was like the path of autonomous systems, right? It's what it is. Like, if you had, something like 1, 2, 3, 4, this would advertise like I'm 4, right? To this one. And this would say like something like 3, 4, right? And this would advertise 2, 3, 4, right? And that's kind of what the AS path is. It's the path of autonomous systems, right? We're going to route to that, right? I showed you cases where the AS path was advertised for some different real world systems, right? We saw that and how some of the hijacking worked because people were advertising false AS paths, right? So we use AS path to determine where our packet's going, who our packet's going to be routed through, right? And we prefer a shorter one, but we don't always make decisions based on the shortest path, right? The other thing is what? The next hop? What's the next hop contain? It's just, the next hop is the router, right? This might be a router here. There's our R4, right? In this case, the next hop is R4 because it's letting it know that 3 says, like, if you want to go to 4, send it to R4, right? If you want to take this route, who do you send it to, right? That's really the next hop is saying, right? So like, this is going to have like R3, and so for this one, the next hop is going to be like R3. Saying like, okay, if 2 decides to take this hop, send it to R3, right? And then if this might have like R2, and so that the next hop would be R2 because now 1 would know, okay, I see this path, I should send to R2, right? And now this can say, okay, now I see this path, I know I can send it to R3, right? And then they can figure out who to send it to that path, right? So we need to find both the path and who do we forward it to get along that path, right? So yeah. Any questions there? Yeah.
Can you go over a bit more between like IBGP and eBGP?
Well, I won't ask you anything on that. That's a little, yeah. I think that's kind of a niche thing, and I think. But IGB, generally, these are all external, like, right? But you could think of like, this could have. Let's say this is this network here, right? R4, right? And it might have other routers in here. This is for A, and this is for B, or something like that, right? And this might learn something, and it might send it through IBGP to this one, because the other BGP routers need to know that. These could be internal routers, and they're not really caring. They could be like OSPF, right? They're not really caring about BGP, right?
So IBGP is really only sent between like 2 BGP.
Yeah, it lets you know like that this learns something new. How do we forward it to this? Because it's a little bit different, right? We're talking internally now, so it's kind of just like there's different constraints of the protocol or what it's trying to do, and I think like I don't know. Yeah, probably like the book doesn't give a great explanation of this, I think, and then I don't know. You don't find a lot of good information online about examples of how IBGP works, really. Most of it's focused on BGP, and I think that's a really interesting thing anyway because it's complex. Any other questions? So I think the only other thing is like SDN we didn't talk about, right? So what are the components of SDN?
Abstraction.
Well, what the components?
Oh.
The goal is really
Control flow.
like increase ability to do abstraction of of kind of the control plane in the data plane, right? Right now they're really closely integrated. We'd like to make them separated, that abstract. So we have basically what? We have, if we look at components, what are they?
The data plane equivalent.
So we have it something like a, yeah, we do have it and this will have a controller, right? So that's one thing, the controller, right, will be on that plane. And this will have just kind of like a switch type thing, or it's a porting device. What will this need to have to do the SDN though? First, I mean, we're missing like at least two things that are kind of important with SDN. So first, this controller has to talk to this, right? I should have this. So what do we need? We need to have some sort of API, right? Which is generally OpenFlow, is a protocol, right? So we need a way a controller can specify to the switch how to operate. And so what does this controller send? Huh? Rules to do what?
Reporting table.
Yeah, it's rules, but they're gonna dictate what? Like, what are the rules gonna say?
Where to send packets?
They're gonna modify. Really, what they're gonna do is they're gonna modify this flow table, right? So we have this table in here, right? And you're right that we have these, rules are going to change this somehow. We're gonna send these commands that they're gonna define what goes on in this table, right? And so that's kind of the key. I think that this flow table, the API, and the controller are kind of the three key things we have in SDN, right? And that this controls. So I think that's what we didn't really do any science in this, so I don't want to push too hard. But that's really the key. Is you should understand that we're abstracting the control, which modifies the flow table, right? The flow table determines what? How do we afford packets in general, right? Based on, this could be based on Ethernet ports, IP, or Ethernet addresses, IP addresses, TCP ports, a number of different things, right? So this can be really vague, and the controller can change any of those, right? Huh? Yeah, this is gonna have basically matching, what to match on. Each entry is gonna have that, what action to take, and then maybe some stats, statistics on how often that's been used, right? I'm not gonna ask you anything in that much detail, but that's the key thing, right? Because that's really all we're doing, all switches do is just make decisions based on that, forward based on that. And we're just abstracting the way our ability to do control however we prefer to using that, right? Any questions? So I think that's everything. So you know that. That's pretty easy, right?
Works on my machine. Thank you, 2 times.
Yeah.
That's right.
So somebody's gotta give me an IP address then, right? You have a host open, so we have a WCU assigned IP.
How about 0.0.0.
Anybody?
It's 172.23.234.8.
That 2.3?
Dot 234. Dot 80.
8.80?
Yeah.
Okay, so we have an IP address and we have a net mask, which is
Oh god, man, I'm looking at it doesn't have a net mask.
maybe.
I have to get installed NetTools. That's what I've got. Dash can. Kill yourself.
Okay,
Dash kills it.
we have
IP. I have config /. On my phone. Let's see if this works.
I have FF F. Okay, which is going to be what's this going to be? 255 dot. You want to guess here? Huh? 40, yeah. 0, right? That's what this is. Or it's a slash what? Huh? 20?
Yeah.
Yeah, it's a slash. Okay. So this would be 16 plus this 4 is 20, right? So it's a slash 20, right? And so if we have this, and this is what I hate doing, so once you do this, we can just say, this is all going to be, it's going to be 172
Doesn't it go?
dot 23, no matter what, because it's this, right? And then this is going to be 234 is, so I think this is 0, 16 plus
1010.
1, 0, okay, 1, 0, okay, that's 134.
Yeah.
And the fact is, this one is actually not going to be used either, right? Because we're in this space. So we're going to have to break up this, and we're going to say slash 20. So our net mask is going to include, I should have drawn this here, 172.23 dot something, and we're just going to write this. We're just going to write it like this, right? So this is, 8. This is 16. So 20 is where? Right here, right? And so if we look at what's in this range, we have 172.23 dot what? Huh? This is 224, right? Right? 224, which is 1110.000, right? Dot 0. Right, so that would be like the lowest address in this range you can have, right? So in fact, I look mine up and I have 228. So mine was at 228, right? Which is obviously greater than 224, so we're okay there, right? And then what's the highest address going to be in this range?
Dude.
223 dot. What is this octet going to be? This last one.
11101111.
Yeah, right. Because this has to be the same, right? That's going to be this has to be the same. The lowest value of this is 0000. That's why this is 224. The highest value, this is 1111, right? And so that's 239, right? Thanks. So that would be the lowest.
2, 3, -1.
That'd be the highest, right?
Really?
So that would have to, so you can compute the range and determine, what the addresses are, right? So that's slash 28. Any questions?